Close your eyes and try to calculate the speed of a falling stone without using the number 0. Or try to gauge the age of a deep canyon without the concept of millions of years. It is almost impossible to do. Our minds need tools to think, and the greatest tools we have ever made are not crafted from stone or steel. They are ideas. These breakthroughs act like invisible software, silently updating the operating system of the human brain without altering our biology. They allow us to see what was once invisible. Tonight, we will trace 50 of these conceptual leaps, moving slowly from the simple invention of 0 to the far edge of the observable cosmos. Settle in, let the room go dark, and let your mind drift through the quiet history of how we learn to understand our world. The concept of 0. Imagine standing in ancient Rome. You are surrounded by grand stone aqueducts stretching across valleys and massive temples built to last for thousands of years. The Romans ruled a vast empire, managed legions of soldiers, and tracked vast amounts of wealth. Yet, if a merchant sold every single one of their coins, they had no way to write down what they had left. They could write down the number 10 or 100 or 1000, but they did not have a single symbol to represent having nothing at all. To them, empty space was simply a void, not a number you could use in calculations. It took a massive shift in human thought to turn nothing into something we could work with. Around the 5th century, in India, mathematicians like Brahmagupta began to look at the void differently. They realized that nothingness could behave like a number, with its own rules and properties. Brahmagupta wrote down a mathematical rule that changed everything. He suggested that if you subtract a number from itself, the result is 0. It sounds simple to us now, but it was a quiet revolution that laid the foundation for modern science. By treating 0 as an actual number, rather than just an empty space on a counting board, mathematics transformed. It allowed for place-value arithmetic, making it easy to write down massive numbers and do complex calculations with just 10 simple digits. Without 0, we would not have coordinate geometry to map our world, or calculus to calculate the paths of moving planets. 0 became the silent engine of science. But this idea did not spread without deep resistance. When 0 arrived in medieval Europe, it was met with fear and suspicion. Church authorities and local governments banned the symbol entirely. They worried it was a dangerous gateway to the vacuum, a concept they associated with heresy, chaos, and the devil. They believed that nature abhorred a vacuum, so a symbol representing nothingness must be dangerous. Merchants had to use it in secret, writing it in hidden ledgers to balance their books. Yet, the power of nothing could not be contained. It eventually reshaped our world, proving that sometimes the empty spaces hold the greatest power of all. Yet, as we learned to balance our accounts with nothingness, a new question arose. What if our very home, the Earth, was not the stable center of everything? The Copernican Shift. In the spring of 1543, in a quiet room in Frombork, Poland, an old man lay dying. His name was Nicolaus Copernicus. On that very day, legend says he was handed the first printed copy of the book he had spent decades writing. It was called De Revolutionibus Orbium Coelestium. He touched the pages, closed his eyes, and slipped away. He did not live to see the storm his pages would unleash. For 1400 years, people looked up at the sky and felt a sense of absolute safety. They believed the Earth was a heavy, immovable anchor, sitting right at the center of everything. Around it, the sun, the moon, and the stars spun in perfect, comforting circles. It made sense to the senses. When you stand outside on a quiet evening, the ground beneath your feet feels solid and still. You see the sun rise in the east and set in the west. It feels natural to believe we are the center of the stage. This belief went far beyond science. It was a comforting story that placed humanity at the absolute heart of a purposeful universe. Copernicus looked at the same sky and saw a different geometry. He suggested that the Earth is not the stationary hub of creation. Instead, he proposed that our world is simply another passenger, spinning on its own axis once every day, and marching in a giant circle around the Sun once every year. The Sun, not the Earth, was the quiet center of our neighborhood. To understand the weight of this change, we have to imagine how the world felt before it. The ground was your foundation. It was the only thing that did not move. When Copernicus set the Earth in motion, he did more than rearrange the stars. He shook the very idea of stability. Think of riding on a ship in calm waters. If you are inside the cabin, it feels as though you are standing still while the shore moves past your window. Copernicus asked humanity to accept that we are all on a giant ship, hurtling through space at a speed we cannot feel, spinning like a top as we go. This was a deeply unsettling idea. If the Earth was moving, why did we not feel the wind rushing against our faces? Why did objects dropped from towers fall straight down instead of landing far behind us? More than that, it shattered the ancient map of reality. In the old view, there was a clear structure to existence. Below was the heavy, imperfect Earth, and above were the pure, unchanging heavens. By turning the Earth into a moving planet, Copernicus dragged our home down into the sky, making it just another wandering rock. This idea threatened to undo the entire social and spiritual order of the time. If the Earth was just another planet, then the heavens were no longer a separate divine realm high above us. The boundary between the earthly and the heavenly began to dissolve. We were no longer looking up at a stage built for our benefit. We were looking out into a vast, indifferent void. This shift removed us from our pedestal. If we were not at the center of the universe, it suggested that the cosmos was not built solely for us. We were suddenly adrift in a vast, silent ocean, clinging to a spinning ball of dust. It was the first time we had to accept that the universe might not care about our comfort, and that reality might be vastly different from what our senses tell us. Universal gravitation. Let us take a moment to imagine a quiet afternoon in late autumn. You are sitting in an orchard in England, watching a ripe red apple slip from its branch and fall softly onto the grass. At the very same moment, the pale curve of the moon is riding high in the afternoon sky. For almost all of human history, people believed these two events had absolutely nothing to do with each other. The apple was made of earthly matter, which naturally fell downward toward its home. The moon was a heavenly body, made of a perfect, unchanging substance, destined to circle the earth forever in a realm governed by completely different rules. Then, a young man sitting in that orchard asked a deceptively simple question. What if the force pulling the apple down does not stop at the top of the tree? What if it stretches out, past the clouds, past the atmosphere, going on and on into the deep void of space? What if that very same pull is what holds the moon in its path? This single idea shattered the old division between the earth and the heavens. It suggested that one set of rules governs everything in the cosmos. To make sense of this, we can think of throwing a stone. If you toss a stone, it curves down to the ground. If you throw it harder, it goes farther before landing. Now, imagine you could throw that stone so fast, with so much energy, that the curve of its fall matches the curve of the earth itself. The stone would keep falling, but it would never hit the ground. It would go all the way around the world. This is exactly what the moon is doing. It is constantly falling toward the earth, but it is moving forward so fast that it keeps missing us, locked in a permanent, beautiful fall. The strength of this invisible bond depends on two simple things: how heavy the objects are, and how far apart they are. If you double the distance between two stars, the pull between them does not decrease by half. It drops to 1/4 of what it was. This mathematical rule connected the falling apple directly to the paths of the planets orbiting the Sun, matching their movements with perfect precision. This realization changed our view of reality. The universe suddenly felt like a grand clockwork machine, a vast system where every gear and lever is governed by predictable mathematical laws. If we know the weight and position of every object, we can calculate where they will be 10 years from now, or 10,000 years from now. It brought a deep sense of order to the wild night sky, turning a chaotic sky into a predictable mechanical dance. But once we realized that the same force pulling an apple governs the planets, we had to ask, how do we actually prove such invisible laws? The empirical method. For a long time, humans believed they could understand the universe simply by sitting in a quiet room and thinking. If you wanted to know how a heavy object fell compared to a light one, you did not go to a tower and drop them. You relied on ancient books, on logical arguments written centuries ago by thinkers like Aristotle. People trusted the power of pure reason, believing the human mind could think its way to the bedrock of reality. But the mind, left to itself, loves to find patterns that are not there. It is easily fooled by its own biases, by optical illusions, and by the comfort of beautiful theories. It is too easy to convince ourselves of things that feel right, but are completely wrong. In the year 1620, a man named Francis Bacon published a book that suggested a different path. He argued that our senses are flawed guides, constantly leading us astray. To find the truth, we could no longer rely on clever debates or old authority. Instead, we had to build a system to test our ideas against the physical world. This was the birth of the empirical method. Rather than starting with a grand theory and trying to prove it, this new way of thinking asked us to start with quiet observation. We observe the world, form a guess, and then test that guess with an experiment. If the test fails, we change the guess and try again. It is a loop that never truly ends, built on a foundation of healthy doubt. Every idea must be tested, and every test must be repeatable by others. This shift changed everything. It took science out of the library and put it into the laboratory. Natural philosophy was no longer about passive contemplation. It became a hands-on dialogue with the universe. If you wanted to understand how water boils, or why a magnet pulls at iron, you did not debate it. You measured it. You built instruments to extend your senses, using glass to reveal the tiny and the far away. You watched, you recorded, and you let the evidence guide you. By accepting that we do not know, and by testing every claim, we began to uncover the hidden machinery of the cosmos, one careful experiment at a time. Deep time. Imagine standing on a rocky cliff on the coast of Scotland, where the cold, grey sea beats endlessly against the stone. In the summer of 1788, a man named James Hutton stood at a place called Sycamore Point. He looked down at the rocks beneath his feet and saw something that troubled his mind. Vertical layers of dark grey shale, pointing straight up towards the sky like ancient teeth, were covered directly by flat horizontal layers of red sandstone. It was as if two completely different worlds had been pressed together. Hutton realized that for those bottom rocks to form, tilt, be worn flat by the sea, and then covered by new sand, must have taken longer than anyone had ever imagined. He wrote that he could find no vestige of a beginning, and no prospect of an end. Before this moment, most people believed the world was very young. A well-known calculation by an archbishop named James Ussher stated that the Earth was created in 4004 before the Common Era. That meant the entire universe was just about 6,000 years old. In that short time, every valley, mountain, and ocean had to be explained by sudden, massive disasters, like giant floods that reshaped the world in an instant. It was a comforting timeline, one that placed humans at the very beginning of the story. But Hutton, and later a scientist named Charles Lyell, suggested something different. They proposed that the Earth is shaped by very slow, gentle forces that we can still see happening today if we look closely. Think about rain washing a tiny grain of sand down a muddy creek, or a river slowly carving a path through solid rock. These forces seem small, almost powerless in our daily lives. But if you give them enough time, they can build vast mountains and carve out grand canyons. This way of thinking is called uniformitarianism. It means the present is the key to the past, and that the same quiet processes we see today have been working since the beginning. This shift in thinking changed everything. If the Earth was shaped by slow erosion and the quiet buildup of dust, then the Earth could not be just 6,000 years old. It had to be millions, even billions of years old. It meant that the history of our world was a vast, silent ocean of time, rather than a short, dramatic play. To understand this, imagine a book with 1 million pages. If that entire book represents the age of our planet, then all of written human history, from the first clay tablets to the screen you are using now, would fit onto the very last sentence of the very last page. We are a brief whisper at the end of a very long night. This realization of deep time was dizzying. It shook our sense of importance, removing us from the center of the timeline just as Copernicus had removed us from the center of space. We were no longer the main characters in a young world, but late arrivals in an ancient one. With the realization of Earth's ancient past, we had to wonder, how did life itself manage to adapt and change over these vast stretches of time? Natural selection. During his long voyage on the ship named the Beagle, Charles Darwin stepped off onto the black volcanic rocks of the Galapagos Islands. He spent his days collecting small birds, pinning them to boards, and writing in his leather journals. At first, they seemed like ordinary birds, similar to the ones he had seen back in South America. But as he compared the finches and mockingbirds from one island to the next, he noticed something strange. The birds on one island had thick, heavy beaks, perfect for crushing hard seeds. On another island, just a short sail away, the same kind of bird had a thin, sharp beak, ideal for probing flowers for nectar. Each bird possessed a beak uniquely suited to the specific diet available on its home island. They were isolated from one another by miles of deep blue water, yet they were clearly relatives. This observation started a quiet revolution in his mind. He began to see how these designs could happen without a designer. Every living creature is born slightly different from its parents. This is random variation, a natural outcome of how life copies itself. One baby bird might have a beak that is 1 millimeter longer than its sibling. In a normal year, that tiny difference does not matter at all. But if a dry season comes, and only the deep hidden seeds survive, that single bird with the slightly longer beak can reach the food while the others cannot. That bird survives, while its siblings do not. When the survivor reproduces, it passes the tiny variation down to its offspring. Over many generations, the average beak size of the entire population changes. This is the engine of natural selection. It is a slow, quiet filter. It combines two simple elements: random variation within a population and environmental pressure. The environment poses a challenge, like a dry winter, a new predator, or a changing forest. The random variations that help an organism get past that challenge lead to the non-random survival of those individuals. The traits that help them survive are passed on, while the others fade away. There is no conscious effort behind this. The bird does not try to grow a longer beak. The environment does not try to shape the bird. Survival is the simple result of physics and biology meeting the world. This idea changed how we view our place on Earth. Before this, people believed that every creature was created in its final, perfect form, placed on a static planet. We saw the world as a finished painting, beautiful and unchanging. But Darwin showed us that life is a moving river. There is no blueprint, no final destination, and no grand purpose driving it forward. There is only a beautiful, relentless adaptation to the present moment. Instead of onlookers watching a finished world, we are participants in an ongoing flow of change that connects us to every creature that has ever lived. We are part of a grand family tree, reaching back to the very first spark of life. Germ Theory. In the year 1847, in the city of Vienna, a young doctor named Ignaz Semmelweis walked the quiet halls of the General Hospital, troubled by a devastating pattern. In the maternity wards, women who had just given birth were dying of childbed fever at terrifying rates. In one ward, where medical students trained, nearly 18% of new mothers lost their lives. In a neighboring ward, run by midwives, the death rate was much lower, only a small fraction of that number. Semmelweis watched closely and noticed a key difference. The medical students were coming straight from performing autopsies in the morgue to delivering babies without washing their hands. He suspected they were carrying something deadly on their fingers. He ordered the students to wash their hands in a simple solution of chlorinated lime before touching the patients. Within a short time, the death rate fell to less than 2%. Instead of celebrating, the medical establishment rejected his findings. They could not accept that their own hands, the hands of respected gentlemen, were carrying death, especially since no one could see what was on them. At the time, people believed that sickness came from bad air, which they called miasma, or from an imbalance in the ancient fluids of the body. They believed that diseases arose spontaneously, appearing out of nowhere from decaying matter. But across the continent, other minds were looking closer at the invisible world. Louis Pasteur, a French chemist, spent long hours studying why wine and beer turned sour. Under his microscope, he saw tiny living organisms multiplying in the liquid. If you heated the liquid, the organisms died, and the liquid stayed fresh. He realized these tiny living things did not appear out of nothing. They came from the environment outside, drifting in on dust particles and settling in the liquid to reproduce. A German physician named Robert Koch took this idea further, looking for the specific causes of human suffering. He wanted to know if a specific creature caused a specific disease, rather than sickness being a general imbalance. He studied anthrax and tuberculosis, isolating the tiny bacteria from sick animals and showing that introducing them into healthy hosts caused the exact same illness. He created a set of strict rules to prove this connection, demonstrating that invisible living microbes were the true source of infection. This shift in thinking changed medicine forever, altering how we view cleanliness and safety. If invisible invaders caused sickness, then we could stop them before they ever entered the body. Doctors began to sterilize surgical instruments, wash their hands, and clean wounds with carbolic acid to keep the microscopic monsters away. Cities began to rebuild their water and sewage systems, separating clean drinking water from waste to prevent the spread of cholera. We began to understand that we share our world with a vast, invisible ecosystem of living organisms, some of which can harm us, and that our best defense is to keep them at bay. Yet, even as we learned to protect our bodies from invisible invaders, we still struggled to share the stories of these discoveries across the world efficiently. The printing press. Let us go back to Mainz, Germany, around the year 1440. In a quiet, dimly lit workshop, a man named Johannes Gutenberg is working with a modified wine press. Instead of crushing grapes for wine, this heavy wooden press squeezes metal letters against paper. Gutenberg has spent years perfecting these tiny, hand-cast metal blocks. Each block carries a single raised letter of the alphabet. He aligns them carefully in rows, coats them in a thick, sticky, oil-based ink, and presses a sheet of damp paper down onto them with force. In a matter of seconds, an entire page of text appears, crisp and clear. It is a process that can be repeated thousands of times, producing identical pages. Before this moment, if you wanted a book, it had to be written by hand. Monks sat in quiet rooms for months, sometimes even years, copying sacred texts stroke by stroke with trembling hands. Because of this slow process, books were rare, precious treasures, affordable only to the very wealthy. Gutenberg changed everything. His new machine could produce pages faster than 100 skilled scribes working all day. Suddenly, the cost of making a book dropped by more than 80%. The monopoly that the church held over knowledge, especially books written in Latin, began to crumble. People did not have to rely on authorities to tell them what was written in important texts. They could read the words for themselves. Soon, printing workshops were opening all over Europe, printing books in the everyday languages that people actually spoke, like German, French, and English, instead of Latin. Mass literacy began to spread across the continent. This shift allowed new, challenging ideas to travel faster than ever before. When a monk named Martin Luther wrote down his criticisms of the church, his words were printed and distributed across Europe in weeks, sparking the Protestant Reformation. At the same time, scientists could now share their findings with colleagues hundreds of miles away, without errors creeping into hand-copied diagrams. They could compare notes and build on each other's work. This rapid, reliable flow of information laid the foundation for the scientific revolution. By turning words into movable pieces of metal, we altered how we make books and how we share our thoughts, opening the door to the modern world and changing human consciousness forever. The self-observing mind. When you feel anger or recall a memory, what is the entity inside you that watches that thought unfold? Think of your mind as a quiet room. Most of the time, we look out the window at the world passing by. But sometimes, we turn around and look at the room itself. We observe the way the light falls on the floor or how the dust drifts in the air. For a very long time, humans thought of this inner room as a sacred, untouchable space, a mysterious soul that could never be measured or mapped. In 1879, in a small university room in Leipzig, Germany, a man named Wilhelm Wundt decided to change that. He established the first laboratory dedicated to studying the mind. Instead of treating our thoughts as theological mysteries, he wanted to see if we could study our inner lives with the same careful, structured focus we use to study the stars or the weather. Wundt trained people to do something very difficult. He asked them to look inside themselves while listening to a clicking metronome or looking at a color. They had to break down their immediate feelings into tiny, basic pieces. Instead of simply saying they liked a sound, they described the exact speed of their reaction and the tiny waves of tension and relaxation that followed it. It was like taking a watch apart to see how the gears turn. Only the gears were their own feelings and memories. This shift changed our relationship with ourselves. Before this work, our inner worlds were thought of as a single, indivisible spark of life. By introducing structured observation to our thoughts, we began to see that the mind is a landscape of many moving parts. We could measure the time it takes for a sensation to reach our awareness, and we could study how one memory pulls another from the dark. We discovered that our minds could be split into two roles, where one part of us experiences the world, and another part stands back to watch that experience happen. Every time we pause to watch our own anger cool down, or trace the origin of a sudden worry, we are using this ability. We are more than players in our own lives. We are the audience too. This capacity to turn our eyes inward, to make the mind both the investigator and the subject, is perhaps the most profound tool we possess. It allows us to step outside the flow of our immediate reactions, giving us the space to understand who we are, one quiet observation at a time. Entropy. Think of a glass of clear, still water. A single drop of blue food coloring falls into it. At first, it is a tiny, concentrated bead of deep blue. Slowly, it blooms into ribbons, spreading out and twisting in the water, until the entire glass turns a uniform, pale blue. The drop has dispersed completely. Now, if a video of this event ran in reverse, it would immediately feel wrong. The pale blue water would slowly separate, the dye gathering itself from all corners of the glass, rising back up to form that single perfect drop. Here is the strange thing. On the level of individual molecules, no law of physics prevents this from happening. The collisions of water molecules could, in theory, push the dye molecules back together. Yet, it never happens. Even over 1 trillion years, the color would never gather back into a single drop. This strange, one-way behavior of our world is explained by a concept we call entropy. It is the core of the second law of thermodynamics. In simple terms, entropy is a measure of molecular disorder, and the law states that in any closed system, disorder always increases over time. There are only a few ways for the dye to form a neat, concentrated drop, but there are countless billions of ways for it to be mixed up and spread out through the water. It is a matter of pure probability. Things scatter because there are simply so many more ways to be scattered than to be ordered. This constant drift toward disorder gives us something rare in physics, which is an arrow of time. Most fundamental laws of nature work just as well going backward as they do going forward. A planet orbiting a star behaves just the same in reverse, but entropy does not. It points us forward. It tells us why a cup falls and shatters, but the shards never leap back onto the table to form a whole cup again. This law applies to more than glasses of water or breaking cups. It governs the entire universe. Right now, the universe is filled with pockets of high order, like burning stars and living planets. But every time a star burns fuel, or you take a breath, the total amount of disorder in the cosmos increases. Eventually, in the very far future, this process will reach its natural limit. All the stars will burn out, all the energy will spread out evenly, and the universe will reach a state of maximum entropy. This is often called the heat death of the universe. In this state, everything will be the same temperature, and no change, no work, and no life can ever happen again. It is a quiet, final equilibrium. If the universe is slowly winding down toward disorder, what happens when we study the smallest, most fundamental building blocks of matter? Quantum uncertainty. For a very long time, we lived with the comfort of a predictable universe. People believed that nature was a grand mechanical clock, ticking away according to set rules. If you could somehow know the position and speed of every single atom in existence, you could calculate the future with perfect accuracy. The past, present, and future were all locked in place, running on track lines that had already been laid down. But in 1927, a German physicist named Werner Heisenberg looked closely at the subatomic world and found that nature does not work like a clock at all. He calculated a mathematical limit to our knowledge, a rule that we now call the uncertainty principle. Imagine trying to find a tiny particle, like an electron, in the pitch dark. To see it, you must shine a light on it. But at this microscopic scale, a single packet of light carries enough energy to knock the electron off its path, like a cue ball striking a billiard ball. The moment you detect its location, you change its speed and direction. If you use a gentler light with less energy, the measurement becomes blurry, and you lose track of its exact position. The more precisely you try to measure where the particle is, the less precisely you can know its momentum. This is not about our technology being imperfect. Even if we built the most advanced measuring tools imaginable, this limit would still exist. It is a fundamental property of how reality is put together, rooted in the wave nature of these tiny particles. At the quantum scale, things do not have a single definite home. Instead, they behave like waves, spread out in a cloud of possibilities. An electron does not exist in one specific spot until we look for it. Until that moment of observation, it exists as a wave of probability, occupying many potential places at once. This discovery dismantled the old idea of a deterministic universe. We had to accept that, at the deepest level of reality, nature is governed by probability rather than certainty. The solid ground beneath our feet is built on a foundation of chance, where things only become definite when they interact with the world around them. The universe is not a clockwork machine, but a quiet game of possibility. If the microscopic world refuses to sit still, what does that mean for the grand fabric of space and time we walk through every day? Special relativity. Imagine you are chasing a beam of light. You speed up, moving faster than a bullet, faster than a rocket, until you are traveling at 186,000 miles per second. If you held a small mirror in front of your face, would you still see your reflection? It feels like the light leaving your face should never catch up to the mirror, leaving you with blank glass. But the reflection remains. The light still leaves your face and hits the mirror at the exact same speed as it would if you were sitting quietly in a chair. In the year 1905, Albert Einstein proposed that the speed of light never changes. It is a universal speed limit, and it behaves the same way for everyone, no matter how fast they are moving. This simple rule forces us to accept a strange reality. If the speed of light is constant, then space and time cannot be. They must stretch and squeeze to keep the speed of light steady for everyone. If you were to watch a spaceship fly past you at near the speed of light, you would notice strange changes. The clock inside the spaceship would appear to tick much slower than your own. The seconds would stretch out, taking longer to pass. The very shape of the ship would be squashed, compressed in the direction it is traveling. To the astronaut inside the ship, however, everything feels normal. Their clock ticks regularly, and their ship remains its proper shape. Instead, they would observe your clock ticking slowly, and your world compressed. Both of you are correct. Motion changes the rate at which your universe unfolds. Because of this, there is no single true measurement of distance or duration. Two events that happen at the exact same moment for you might happen at different times for someone else moving past you. The order of events depends entirely on where you are and how fast you are traveling. For centuries, scientists followed the idea of a universal clock. They believed that time was a steady stream flowing at the exact same pace everywhere, a master clock ticking for the entire cosmos. Special relativity shattered this idea. It revealed that time is not a fixed background. It is elastic, bending and stretching depending on your speed. A second for you is not the same as a second for someone else. Space and time are woven together, creating a universe where your journey shapes the rate at which you age. We live in a world where speed alters the passage of your hours and the length of your steps. The circulatory system. If we look at a modern city, we see water flowing through pipes, returning to treatment plants, and pumping back out in a continuous recycling loop. For a very long time, people thought the human body worked in a completely different way. They imagined the body as a fireplace. In this old view, food went into the stomach, turned into blood in the liver, and then traveled outward to the organs, where it was completely burned up like wood turning to ash. This meant the liver had to constantly manufacture brand new blood, day and night, to keep the fire going. This idea, created by an ancient Greek physician named Galen, ruled medicine for 1400 years. Nobody questioned it. Then, in 1628, an English doctor named William Harvey published a small book with a Latin title, De Motu Corde, which translates to On the Motion of the Heart. Harvey did something simple but radical. He measured how much blood the heart actually pumps in a single hour. He calculated that in just 1 hour, the heart pumps more blood than the entire weight of a human being. It was mathematically impossible for the liver to create that much blood from the food we eat. There was simply not enough food or space to make it happen. Harvey realized there was only one logical explanation. The blood had to be moving in a closed circle. Instead of being consumed like fuel, the blood was being recycled. The heart was not a furnace, but a muscular pump. It pushed blood out through the arteries, and that same blood returned to the heart through the veins, over and over again, in a one-way loop that never ends as long as we are alive. This single realization changed how we see ourselves. It turned the human body from a mysterious, consuming fire into a beautiful system of plumbing and pressure. We began to see our organs as connected parts of a single, flowing machine. As you lie still tonight, you can feel this quiet pump at work, recycling the same ancient river inside you, beat after beat, keeping the cycle going in the quiet dark. The double helix. A twisted, microscopic ladder holds the instructions for everything you are. It is so small that millions of them could fit on the head of a single pin. The rungs of this ladder are made of only 4 repeating chemical bases, which scientists call adenine, thymine, cytosine, and guanine. These 4 simple components, arranged in different sequences, encode the blueprints for every living thing on Earth, from the grandest redwood tree to the quiet beat of your own heart. It is the operating system of the natural world, running quietly in the background of every moment. For a long time, humanity knew that traits passed down through generations. We knew that parents passed characteristics to their offspring, carrying the physical variations that Charles Darwin observed in his work. We knew the message was traveling, but we did not know what the envelope looked like, or how the words were written. The physical library of life remained locked away in the dark. That changed in the middle of the 20th century. In 1953, a group of researchers set out to solve this puzzle. Rosalind Franklin, a brilliant chemist, captured a historic image known as Photo 51. By shining X-rays through crystallized fibers of deoxyribonucleic acid, she captured a ghostly, shadowed cross on a piece of photographic film. It was a delicate signature of light and shadow. When James Watson and Francis Crick saw this pattern, they recognized the secret shape it revealed. It was a double helix, 2 long strands winding around each other in a gentle, endless spiral. This shape did far more than resolve a structural puzzle. It solved the mystery of life itself. The magic of the double helix lies in its perfect symmetry. When the cell needs to copy its instructions, the twisted ladder unzips down the middle, splitting the rungs in half. Because each chemical base only pairs with one specific partner, each single strand automatically holds the exact information needed to rebuild its missing half. One template becomes 2 identical copies, passing the spark of life forward without losing a single letter of the code. It is a system of replication that is both elegant and simple, allowing life to persist and grow. Every cell in your body contains this library of instructions, a quiet inheritance stretching back through billions of years of history. It is the physical thread that connects us to every creature that has ever lived, a quiet whisper from the deep past. But knowing the blueprint of life was only half the puzzle. What of the tiny, indivisible pieces that make up the physical universe itself? atomic structure. In 1911, a scientist named Ernest Rutherford set up an experiment in his laboratory that would change how we feel about the physical world forever. He fired tiny, fast-moving particles at a sheet of gold foil that was extremely thin, expecting them to pass straight through like bullets through paper. For the most part, they passed through without any trouble. But a few of these particles did something completely unexpected. They bounced straight backward, returning toward the machine that had fired them. Rutherford later wrote that it was the most surprising event of his life, comparing it to firing a 15-inch artillery shell at a piece of tissue paper, only to have it bounce back and hit you. Before this moment, science described the atom as a solid object, a soft sphere of positive charge, with negative charges scattered throughout like plums in a pudding. Rutherford realized the reality was far stranger. The atom was not a solid ball at all, but rather a structure of open pathways. It was almost entirely empty space. At the very center lay a tiny, dense core, containing almost all of its mass, which we now call the nucleus. Floating far away from this central point were even tinier electrons, orbiting in the vast, quiet emptiness. If you scale these components up to make the distances easier to understand, the proportions are dizzying. If the nucleus of an atom were the size of a single marble sitting on the 50-yard line of a large sports stadium, the outer edge of the atom would be the outer walls of the stadium. The electrons would be like tiny dust motes buzzing around the very top rows of the seats. Everything in between that marble at the center and those dust motes at the edge is completely, utterly empty. This realization is strange to sit with, especially when the house is quiet. The chair you are sitting on, the floor beneath your feet, and even your own hands feel solid and permanent. Yet they are 99.999% empty space. When you place your hand on a table, you are not actually touching solid matter. Instead, the empty atoms in your hand are repelled by the empty atoms in the table. The electrostatic forces of the electrons push against each other with immense strength, creating the physical illusion of contact. We spend our lives walking around on a world of ghosts, held up only by these invisible fields of force, floating over a vast and silent void. The unconscious mind. Imagine a massive iceberg drifting in the dark waters of the Arctic Ocean. Above the surface, a sharp, glittering peak of ice catches the faint moonlight. It looks solid, complete, and self-contained. Yet, beneath the black water lies the real giant. 9/10 of the iceberg is hidden in the freezing depths, unseen and untouched by the wind. We only see what is exposed, ignoring the massive weight resting below. This is the image Sigmund Freud used to describe the human mind. The small tip above the water is our conscious awareness. It is where we make conscious decisions, think through our daily problems, and feel like we are in total control of our lives. But underneath lies the vast unconscious. This dark, silent space holds our deepest fears, forgotten memories, and instinctual drives. It is a massive storehouse of things we have pushed away because they were too painful, too frightening, or too chaotic to face. Before this idea took hold, many thinkers believed that humans were entirely rational creatures. The prevailing thought was that we had complete control over our minds, acting as the absolute masters of our own thoughts. We believed we could look inside ourselves and see everything that made us tick, explaining every choice with reason. This view gave us a comfortable sense of complete free will and self-determination. We assumed that the human mind was fully transparent to itself, leaving no room for mysteries hidden inside our own heads. The discovery of the unconscious shattered that confidence. It suggested that we are not entirely the masters of our own houses. Instead, our conscious choices, our likes and dislikes, and even our sudden changes in mood are often directed by the silent currents flowing deep beneath the surface. We might think we choose a career, a partner, or a goal for logical reasons, but we are actually being nudged by forces we cannot see, forces shaped by old memories and hidden desires. This changed how we understand ourselves. It meant that self-knowledge is not a simple task. We cannot look inward and find all the answers easily, because the most powerful parts of who we are remain hidden in the dark. We are deep, complicated puzzles, driven by whispers from a place we cannot easily reach, constantly influenced by the silent giant below. Fiat currency. Why does a baker hand you a warm, crusty loaf of fresh bread in exchange for a small, green slip of printed paper? You cannot eat the paper. You cannot wear it to keep warm, and you cannot use it to build a shelter. Yet, the baker accepts it without hesitation, wraps your bread, and sends you on your way. For most of human history, money was something you could touch and value for what it was. People traded with seashells, salt, or heavy coins pressed from gold and silver. These coins carried weight because the metal itself was rare and useful. If a kingdom fell, the gold coin still held value, because it could be melted down into a shiny ring or a cup. The value lived inside the object itself. Slowly, we moved away from these heavy metals. We created paper receipts that represented the gold sitting safely in a secure vault. But today, the system has transformed completely. The paper in your pocket, or the digital numbers on your phone screen, represents nothing physical at all. No vaults of gold back them. We call this fiat currency. The word fiat comes from a Latin phrase meaning, "let it be done." It exists because a government declares that it is legal tender, and we all agree to act as if that declaration is a fact. The value does not belong to the material. It belongs entirely to the declaration. This entire global economy runs on a shared story. We have agreed on a collective belief. When you hand over that slip of paper, you are offering a promise. And the baker accepts it because they trust that the next person will do the same. This trust acts like an invisible web connecting millions of strangers every single second. Without this mutual agreement, the paper returns to being just paper, and the digital numbers become quiet pixels on a screen. Because we trust in the stability of our institutions, we can trade across oceans, build houses on credit, and plan for a future years down the line. It is a quiet agreement that holds the modern world together, a silent trust that turned simple paper into the lifeblood of human civilization. We have built our entire world on the strength of a shared promise. Double-entry bookkeeping. Imagine walking through the stone streets of Venice in the late 15th century. The docks are busy, filled with ships carrying spices, silk, and wood from distant lands. For a long time, merchants kept track of their business in simple, messy lists. They wrote down who owed them money and what they spent, but they never really knew if they were making a profit until the very end of a long voyage. Then, in 1494, a Franciscan monk named Luca Pacioli published a book. He did not invent the system inside it, but he was the first to write it down. It was a simple method used by Venetian merchants, and it changed the way we track human effort. We call it double-entry bookkeeping. The idea is elegant. Every single transaction has two sides, like a coin. Nothing happens in isolation. If you buy a sack of grain, two things change. You have more grain, but you also have less cash. In this system, every event is recorded twice. One record is a debit, which shows what comes in. The other is a credit, which shows what goes out. These two sides must balance each other out perfectly, creating a mirror image of the transaction. Think of the ledger as a scale. On one side are your assets, the things you own. On the other side are your liabilities, the money you owe to others combined with your equity, which is your own share of the business. When you add them up and subtract one side from the other, the result must always be zero. Zero acts as the quiet center, the point of perfect balance. If the system does not return to zero, a mistake has been made somewhere in the pages. This simple rule did something profound. It gave merchants a clear, objective picture of their business at any moment. They could see their profit and loss without waiting for a ship to return. This clarity created trust. Because people could trust the books, they began to pool their money together. They created the first joint stock corporations. They built global trade networks. Modern capitalism was born from these balanced pages. A simple bookkeeping method did more than count wealth. It helped build the modern world. Curved space. Imagine a large, flexible sheet of thin rubber stretched tight, suspended in the air. Now, imagine placing a heavy steel bowling ball right in the center. The heavy weight of the ball immediately pulls the rubber downward, creating a deep, sloped depression in the fabric. If you were to gently roll a few small glass marbles across the sheet, they would not travel in straight lines anymore. Instead, they would roll along the slope, curving and spiraling toward the heavy ball in the center. It looks like the bowling ball is pulling the marbles, but the marbles are simply following the shape of the surface beneath them. For a long time, we thought of gravity as an invisible, instantaneous pull. Sir Isaac Newton described it as a force acting across the empty vacuum of space. But in 1915, Albert Einstein offered an explanation that transformed our understanding of the universe. He suggested that space and time are not a static stage where events happen. Instead, they are woven together into a single, flexible fabric called spacetime. Under this view, gravity is not an active pull. It is the shape of this fabric. When a massive object like our sun sits in spacetime, it warps the fabric around it, just like that bowling ball on the rubber sheet. When the Earth orbits the sun, it is not being pulled by an invisible tether. It is simply rolling along the straightest possible path through a valley of curved space. This concept explains that mass and energy tell spacetime how to curve, and curved spacetime tells mass how to move. A falling apple or an orbiting moon is just following the shape of the local geometry. Even light, which has no mass, bends its path as it travels through these cosmic valleys. The empty space around us is not empty at all. It has a structure, a geometry that bends, stretches, and ripples in response to everything that moves through it. This shifted our view of the cosmos. We no longer live in a rigid, flat universe where forces reach out across a void. We live in a soft, dynamic world where the paths of planets, stars, and even light itself are guided by the unseen curves of the space they inhabit. Every single step we take is a gentle reaction to the shape of the Earth warping the space right beneath our feet. Chemical anesthesia. Imagine the dread of entering a hospital in the early 19th century. Before the middle of that century, operating rooms were places of loud, desperate terror. Patients were strapped tightly to heavy wooden tables to keep them from struggling. Surgeons had to work with frantic speed, sometimes amputating a limb in under 60 seconds. The main goal was simply to finish the operation before the patient died from the sheer shock of the physical agony. In those days, a surgeon was judged not by their gentleness, but by the speed of their hands. Everything changed on a quiet autumn morning in 1846. A dentist named William Morton walked into a crowded operating theater in Boston, holding a glass vessel filled with a sweet, chemically altered fluid called ether. A patient sat in the chair, preparing for a painful operation on his neck. Morton had the patient breathe the heavy vapors. Within minutes, the patient drifted into a deep, quiet sleep. The surgeon performed the operation, and when the patient woke, he looked around and announced he had felt nothing at all. This place, now known as the Ether Dome, became the birthplace of a new era. Shortly after, another doctor named James Young Simpson introduced chloroform, which offered a similar escape from pain, even during childbirth. What these chemicals did was shut down the communication lines of the body. Normally, when the flesh is cut, nerve pathways send urgent electrical alarms traveling up to the brain. Anesthesia acts like a soft barrier, silencing those signals before they can register in your awareness. By temporarily turning off the conscious mind, doctors could work on the human frame without causing suffering. This shift transformed the nature of surgery. It stopped being a rushed, brutal race against the clock. Because patients lay still and peaceful, surgeons could finally take their time to explore, repair, and heal. When this ability to work slowly was eventually combined with clean, sterile practices, the modern operating room was born. It turned surgery from a desperate gamble into a quiet, precise science of healing. Human rights. In the late summer of 1789, the streets of Paris were alive with a strange and heavy energy. The old world of absolute kings was crumbling. During those tense and warm days, a group of representatives gathered to write down a simple, radical document. They called it the Declaration of the Rights of Man and of the Citizen. In its lines, they proclaimed that every person was born with an equal claim to liberty, property, and security. Before this moment, the way societies worked was very different. Think of a tall ladder, where your place on the rungs was decided long before you drew your first breath. If you were born near the top, the king could hand you special privileges, much like gifts. These privileges were not yours because you were human. They belonged to you only because of your family name or your wealth. If the ruler changed his mind, those privileges vanished in an instant. But then, a quiet and powerful idea began to spread. They started to talk about natural law. They proposed that some things belong to you simply because you exist as a living human being. You do not need a crown to grant these things to you, and no government can rightfully take them away. This was like discovering a law of gravity for the human soul. It suggested that we possess an invisible, permanent value built directly into reality. This shift in thinking changed the course of history. It was the spark that lit the fires of the American and French revolutions. People began to demand that laws protect these natural qualities rather than grant them as favors. Over the decades, this concept grew, traveling across oceans. In 1948, after the world had gone through a terrible war, nations came together to sign the Universal Declaration of Human Rights. It was a promise that every human life has dignity, no matter who they are. It is strange to think that an idea you cannot see or touch can rewrite the map of the world. It reminds us that we are more than just physical bodies moving through space. We are bound by a shared, invisible worth. If human minds possess inherent rights, does that mean we can build mechanical minds to carry out our calculations? Universal computation. Imagine a summer afternoon in 1936. A young mathematician named Alan Turing is resting in a meadow in Cambridge, letting his mind wander. He is thinking about a machine. This is not a machine made of brass and steam, but a machine made of pure thought. In his mind, this machine has a very long strip of paper tape divided into neat little squares. A small scanner slides over the tape, reading one square at a time. The squares can either be blank, or they can have a simple symbol written on them, like a 0 or a 1. The scanner can read the symbol, change it, and move the tape one step to the left or to the right, following a basic set of instructions. At first, this sounds almost too simple to do anything useful. A person might think such a device could only do one basic task, like adding two numbers together. If you wanted to do a different task, you would have to build an entirely different machine with different gears. But Turing realized something that changed our world forever. He realized that you could write the instructions for any specific machine onto the paper tape itself. This meant you did not need 1,000 different machines for 1,000 different tasks. You only needed one machine, a single device that could read the instructions stored on the tape and simulate any other machine you could ever describe. He called this the Universal Turing Machine. It was a machine that could mimic any other machine, simply by reading a new set of instructions from the paper. Before this idea, a machine was defined by its physical shape. A calculator was a box of gears that could only calculate. A typewriter was a collection of levers that could only print letters on a paper sheet. Turing turned this physical world upside down. He showed that the physical hardware did not need to change. The power was not in the wood or the metal, but in the logic of the symbols written on the tape. By changing the symbols, the machine could become a calculator, a typewriter, a music player, or a translator. It was the birth of software. This single idea is the foundation of the modern computer. Every device we use today, from the phone in your pocket to the massive servers that power the internet, is simply a variation of that imaginary paper tape in a Cambridge meadow. We no longer had to rebuild the machine to change its purpose. We only had to change the thoughts we fed into it. We transitioned from a world of physical machinery to a world of pure, flowing logic, where a single device can become anything we can write down. It is a quiet kind of magic, one that began with a paper tape in a quiet meadow and ended by reshaping the modern world. Chaos theory. For a long time, we believed that if we knew the rules of nature and the starting point of any system, we could predict its future forever. We thought of the universe as a giant, orderly clock. But in 1961, a meteorologist named Edward Lorenz walked to his computer to run a simulation of the weather. He wanted to save time, so instead of typing the full number of 0.506127, he rounded it slightly to 0.506. It was a tiny change, smaller than a breath of wind. Yet, as the machine calculated, this microscopic difference grew. It doubled, then doubled again, cascading through the equations. In the simulation, that tiny variation created a completely different storm system. This is the origin of what we call the butterfly effect. The idea that a butterfly flapping its wings in one part of the world can cause a tornado weeks later in another. Imagine trying to predict where a single leaf will land as it falls from a tree on a windy autumn day. Even if we knew the weight of the leaf and the force of the wind, the tiny bumps on its surface and the microscopic changes in the air currents would send it spinning in ways we could never calculate. What makes this concept so unsettling is that these systems are not random. They follow strict, precise physical laws. Every step is determined by the step before it. Yet they defy long-term calculation because the slightest inaccuracy at the start ballooned into total unpredictability. You can experience this by hanging a simple weight from another weight, creating a double pendulum. When you push a regular pendulum, it swings back and forth in a reliable pattern. But when you add that second joint, the motion becomes wild and impossible to foresee. Even if you try to drop it from the exact same height twice, the tiniest difference in your hand will send the metal swinging on a completely different path. The same thing happens on a giant scale when three stars orbit one another. Their gravity pulls them into a dance so complex that no computer can calculate where they will be in the distant future. We are left with a universe that is completely orderly, yet forever unpredictable. The dream of a clockwork world is gone, replaced by a deep, quiet mystery. Standardized time. In the mid-19th century, a traveler arriving at a railway station in England would often notice a strange problem. Their pocket watch might show one time, while the station clock showed another, and the local town clock down the street showed something else entirely. Back then, time was local. It was set by the sun overhead in each specific town. If you walked a few miles east or west, the time changed by a few minutes. For thousands of years, this did not matter. A horse and carriage moved slowly enough that a 4-minute difference between two towns was invisible. But when iron steam engines began running across the countryside at 40 miles an hour, this patchwork of local times became dangerous. Two trains sharing a single track could easily collide if their drivers were operating on different versions of 12 o'clock. Safety demanded a change. In 1847, the railway companies decided to sync their clocks to a single standard based on the Royal Observatory in Greenwich. They called it Greenwich Mean Time. This railway time spread quickly, but it was not welcomed by everyone. Some towns resisted standard time for years, keeping two different minute hands on their town hall clocks. One hand showed the local solar time, while the other showed the new railway time. It was a strange period where people lived in two different moments at once. Eventually, the need for order won. By 1884, representatives from across the world gathered to divide the entire planet into 24 distinct time zones. With this agreement, the world began to share the same invisible grid. This change did something profound to the human mind. For our entire history, we had lived by the organic rhythm of the earth. We woke when the sun rose, worked while it was light, and slept when the dark fell. Time was a fluid, local experience. But standardizing time pulled us out of the sky and placed us into an artificial machine. We began to live by the clock rather than the sun. It allowed global shipping networks to align and factories to run on precise shifts, but it also detached us from our immediate surroundings. We traded the natural flow of day and night for a synchronized global grid, changing forever how we work, travel, and sleep. The cosmic beginning. For a long time, we thought of the cosmos as a permanent house. The walls were fixed, the ceiling was set, and everything within it simply drifted in place forever. But in the year 1929, an astronomer named Edwin Hubble pointed a telescope at the sky and saw something that broke that quiet picture. He noticed that the light coming from distant galaxies was stretched out. When light moves away from you, its waves stretch, turning a deeper shade of red. The farther away the galaxies were, the faster they were rushing away. The universe was not sitting still. It was expanding, growing larger by the second. If you watch a movie of a cup falling and shattering, and then play it in reverse, all the broken pieces start to rise from the floor and come together again. If the universe is expanding today, it means that yesterday it was smaller. A year ago, it was smaller still. If you wind the clock back far enough, past the birth of our planet, past the first stars, all of space begins to crowd together. All the galaxies, all the empty space between them, and every speck of matter that would eventually form your own body must have once been packed into a single, intensely hot and crowded point. This means the universe had a beginning. It was not always here. Roughly 13.8 billion years ago, everything we know erupted from that single point. It was not an explosion of matter into an empty room. It was the sudden, rapid creation of space itself. Time itself started at that very moment. It is strange to think that there was a day without a yesterday. Before that moment, the concept of time did not exist. There was no before. The cosmic beginning challenges our minds because we are used to things having a cause, a history, a background. To realize that everything, even the vacuum of space and the flow of time, has a starting line changes how we feel about our place in the cosmos. We are living inside an event that is still happening. The expansion that started 13.8 billion years ago has not stopped. The universe is still stretching, carrying the distant galaxies further into the dark, leaving us to look back at the faint light of the beginning, wondering what started the clock. This cosmic beginning means that we are not living in a static, eternal museum. We are part of a story that has a beginning, a middle, and an end. The stars we see at night are not permanent fixtures, but temporary lights that lit up long after the first day, and will eventually fade. We are riding a wave of expansion that began in a tiny, crowded point, drifting in a bubble of space that is still blowing outward into the quiet dark. Active immunization. In the late spring of 1796, in the quiet English countryside, a doctor named Edward Jenner performed an experiment that sounded highly dangerous. He had noticed that milkmaids, who frequently caught a mild disease called cowpox from their cows, seemed completely immune to the deadly smallpox. To test this, Jenner collected a small amount of liquid from a fresh sore on a milkmaid's hand. He then took this liquid and scratched it into the skin of an 8-year-old boy named James. The boy developed a mild fever for a day or two, but he quickly recovered. Then came the true test. Jenner exposed the young boy to actual smallpox, one of the most feared killers of the age. The boy did not get sick. He was completely unharmed. This experiment succeeded because of a beautiful hidden system inside us. Our bodies are protected by a quiet army of cells, constantly patrolling our blood and tissues, searching for foreign invaders. When a new virus enters our system, these defense cells must learn how to fight it. They work to design highly specific proteins, which we call antibodies, to lock onto the invader and neutralize it. But building this defense takes time, and during that delay, the virus reproduces and makes us ill. Jenner realized we could give our defense system a safe head start. By exposing the body to a weakened, harmless version of a germ, we provide a practice run. The defense cells inspect the weak invader, learn its shape, and create the necessary antibodies without us ever experiencing the disease. They store this memory away, keeping a record of the invader's unique signature for years, sometimes even for a lifetime. If the real dangerous disease ever tries to invade, the body recognizes it instantly. The defense army already has the blueprint, and they destroy the threat before we even notice it. This shifted the entire focus of medicine. Instead of waiting for people to fall ill and trying to cure them, we began teaching the body to protect itself beforehand. It was no longer about fighting a battle after the enemy had breached the gates, but about teaching the body to build its own walls. Over the next 2 centuries, this simple method of training our immune system allowed us to completely erase smallpox from the face of the earth and bring other paralyzing diseases like polio to a halt. We turned our own biology into a shield. Synthetic polymers. In 1907, a chemist named Leo Baekeland sealed 2 smelly chemicals, phenol and formaldehyde, inside a heavy iron pressure cooker. He heated them under intense pressure, applying heat and force to coax the molecules into a new arrangement. When he opened the vessel, he did not find a liquid or a gas. Instead, he found a dark, solid substance that had taken the shape of the container, hard and shiny. He called it Bakelite. It was the first completely synthetic plastic. Up to that point, everything humans built was shaped from things already found in nature. We carved wood, shaped clay, and spun wool. But Baekeland had done something different. He had linked small, carbon-based molecules into long, repeating chains. In chemistry, these small units are called monomers, and the long chains they form are polymers. Think of it like paper clips. On its own, a single paperclip is small, flimsy, and easily lost. But if you hook thousands of them together, you get a long, flexible, and tough chain. Because these chains are held together by very strong chemical bonds, they do not behave like natural materials. They do not rot when wet, they do not rust in the air, and they do not dissolve in water. They are practically immortal. Suddenly, humans were no longer limited by what the Earth could grow or provide. Before this, billiard balls were made from the tusks of elephants, and cones were carved from tortoise shells. Now, we could manufacture our own materials in giant vats, designed to be whatever shape or strength we needed. It was a massive leap. We filled our homes and lives with lightweight, durable creations. Yet, this exact durability created a new reality. Because these synthetic chains are entirely alien to nature, the bacteria and fungi that break down dead wood and leaves do not recognize them. The very strength that made these materials so useful means they do not go away. Almost every piece of synthetic plastic ever made still exists, somewhere on our planet, floating in the oceans or buried in the soil, slowly breaking down into smaller pieces, but never truly disappearing. But as we filled our physical space with synthetic creations, we began to wonder if we could build an artificial version of thought itself. Artificial intelligence. Imagine sitting across a dark wooden table, staring at a grid of 19 lines by 19 lines. For thousands of years, humans have played the ancient game of Go on this simple board. The possibilities are so vast that there are more potential board positions than there are atoms in the observable universe. In the year 2016, a man named Lee Sedol, one of the greatest players to ever live, sat down to play against a computer program called AlphaGo. 19 years before that game, another computer named Deep Blue had beaten the world chess champion Garry Kasparov. But Deep Blue was a giant calculator. It followed strict logical rules written by human programmers, searching through millions of moves ahead, choosing the best path like a machine reading a map. AlphaGo was different. Its creators did not teach it how to play Go. Instead, they built a network of artificial neurons and let the machine play against itself millions of times. It learned from its own experience, finding patterns and strategies that no human had ever discovered. During the match, AlphaGo made moves that no human teacher would ever recommend, moves that looked like mistakes but turned out to be strokes of quiet genius. This shift marks a deep change in how we build systems. In the past, we wrote step-by-step instructions. We told the machine exactly what to do, using rules and logic. But our own minds do not work this way. You do not look at a picture of a dog and run through a checklist of rules to identify it. You simply recognize it. Modern machine learning works more like your eyes and your brain. We build digital webs of connections, millions of tiny dials that can be turned. We show the system thousands of pictures of dogs and cats. At first, the dials are set randomly and the machine guesses incorrectly. But each time it makes a mistake, the system adjusts those dials slightly, strengthening some connections and weakening others. Over time, the dials settle into a configuration that can identify a dog instantly. The programmers themselves do not know what the exact settings of the millions of dials mean. The machine has taught itself. This challenges something deep within us. We used to believe that reasoning, creativity, and learning were unique to biological brains. We thought our consciousness was the only flame capable of understanding the universe. If a structure of silicon and electricity can learn to paint, to write, and to defeat our greatest minds at our oldest games, we are forced to ask a quiet question. Is intelligence bound to biology? Perhaps thinking is not a property of organic cells, but a property of patterns, regardless of what medium those patterns are written in. We are looking into a mirror of our own making, wondering if what looks back at us is beginning to feel the warmth of the light. Game theory. Imagine two people locked in separate, quiet rooms. They are accused of a crime, and the police offer each of them a deal. If one betrays the partner while the partner stays silent, the betrayer goes free, while the silent partner gets 10 years in prison. If both stay silent, they both get only 1 year. But if both betray each other, they both get 5 years. Why do they almost always choose to betray each other, even though staying silent would lead to a much shorter sentence for both? This puzzle is the classic prisoner dilemma, and it lies at the heart of a field called game theory. A mathematician named John Nash helped explain why this happens. He described a state of balance where neither player has any reason to change their plan on their own. In this setup, betraying the other person is the only choice that makes sense for an individual. Because no matter what the other person does, betrayal protects you from the worst outcome. When both people reason this way, they end up locked in a stable but less than ideal situation, now known as a Nash equilibrium. This mathematics is not a simple game. It describes how the world works when people, companies, or even nations have to make decisions. Consider 2 giant companies selling oil. If they both keep prices high, they both profit. Yet the urge to undercut the competitor to steal customers often drives both to lower their prices, cutting into the profits of both. We saw this play out on a global scale during the Cold War. 2 massive nations built stockpiles of nuclear weapons. If one side disarmed, it risked destruction. If both disarmed, the world would be safer. But because neither could trust the other, both chose to keep building more weapons, leading to a tense, stable standoff. Even in nature, we see these rules. 2 animals competing for food must decide whether to fight or share. Evolutionary biology shows us that animals often settle into behaviors that look like calculated strategies, balanced to ensure survival. It turns out that mathematics can map the silent negotiations we carry out every day, revealing how cooperation can fail and how we might find our way back to it. Linear perspective. A draftsman sits at a heavy wooden table, holding a straight wooden ruler and a piece of charcoal. On the flat paper before him, he draws a single straight line across the middle to represent the horizon. Right in the center of that line, he presses his charcoal to make one tiny dot. From that single dot, he draws lines that fan outward toward the edges of the page, like the rays of a setting sun. When he draws a row of columns along those lines, they seem to shrink as they get closer to the center. Suddenly, the flat paper seems to tear open, revealing a deep corridor that stretches far into the distance. This is the magic of the vanishing point, a simple trick of geometry that changed how we see the world. Before the early 15th century, drawings and paintings did not look like the real world. If an artist painted a king standing next to a castle, the king might be taller than the towers, because the king was more important. Space was flat, symbolic, and spiritual. But in Florence, Italy, an architect named Filippo Brunelleschi wanted to capture the physical world exactly as the human eye experiences it. He stood outside a stone baptistry and used a small painted panel with a tiny peephole drilled through the back. By holding a mirror in front of the painting, he could compare his painted lines directly with the real building. He discovered that if you project straight lines from your eye to the edges of an object, they all meet at one single point on the horizon. This simple experiment did more than change painting techniques. It shifted the way human beings thought about their place in the universe. By using geometry to map three-dimensional space onto a flat canvas, we started looking at the world through a rational lens. The viewer became the center of the scene. Instead of looking at flat icons from a detached perspective, we were now looking through a window into a realistic, orderly world where space could be measured, understood, and mastered. Symbolic language. Imagine a small group of early humans sitting around a flickering fire tens of thousands of years ago. The forest around them is pitch black and silent. One of them makes a specific, low vocal sound, perhaps a sharp grunt, but there is no predator in sight. In that moment, a quiet miracle happens. The others do not look around in immediate panic. Instead, they understand. The sound represents a threat that is somewhere else, maybe near the river they crossed yesterday, or perhaps a threat that might return tomorrow. By doing this, those early humans did something no other creature had ever done. They turned a simple sound into a symbol. Animals communicate all the time. A bird warns its flock of an approaching hawk with a sharp cry. A dog growls to defend its bone. But these signals are reactions to what is happening right now, in the immediate environment. The bird cannot chirp about the hawk it saw yesterday afternoon, or warn the flock about a hawk that might arrive next week. Their communication is locked in the present moment. Human language broke those chains. We have the ability to talk about things that are far away in space and time. This is called displacement. We can discuss the distant past, plan for the far future, and describe places we have never seen. We can tell stories about lands that do not even exist. We also have a unique way of building sentences, a structure that allows us to stack thoughts inside other thoughts. We can say, "I think that she believes he is lying." This ability to nest ideas inside one another allows us to create infinite meanings from a limited set of sounds. We can build complex, winding thoughts that carry detailed maps of the world from one brain to another. Because we can use symbols, we did more than build shelters and tools. We created a completely new layer of reality. This is a shared virtual world made of ideas. Think about a paper banknote. It is just a piece of paper, but we all agree it holds value. Think about the rules of a game, or the laws of a nation, or the stories of our ancestors. None of these things exist in the physical world. You cannot touch a law or hold a myth in your hand. Yet, they govern our lives completely. This shared world of symbols is what allows millions of strangers to cooperate. We can build cities, run hospitals, and send probes to the edge of the solar system because we share the same stories, rules, and beliefs. Every word we speak is a bridge. We take a breath, vibrate our vocal cords, and shape the air. That shaped air travels across the room and enters another person's mind, carrying thoughts across space. It is a bridge built out of nothing but sound and shared agreement. Logarithmic scales. Let us think about how we measure the vast differences in the world around us. In 1614, a Scottish mathematician named John Napier introduced a system designed to make astronomical calculations much easier. He found a way to turn difficult multiplication problems into simple addition. This was the birth of the logarithm, a tool that compresses giant numbers into sizes our minds can easily hold and understand. At its heart, a logarithmic scale does not count by adding 1, 2, 3. Instead, it measures steps that multiply. Think of the way we measure earthquakes or the loudness of sound. If you have an earthquake of magnitude 5 and another of magnitude 6, the second one is not slightly stronger. It is 10 times more powerful. A magnitude 7 is 10 times stronger than 6 and 100 times stronger than 5. By using powers of 10, which rely on our familiar system of place value and the use of 0 to mark position, we can map out massive, violent shifts on a simple, gentle scale of 1 to 10. Our own bodies use this exact shortcut every single day. Your senses are built to work logarithmically. If you are sitting in a dark room with a single burning candle and someone lights a second candle, you notice a big change in the brightness. But if you are standing outside under the bright midday sun and someone lights a candle next to you, you will not notice any difference at all. The sun is hundreds of thousands of times brighter than a candle, yet your eyes can adjust to receive both. Your brain compresses the massive flood of light so you can navigate the world without being overwhelmed. We do the same with sound. We hear a whisper and a thunderclap on the same sensory dial, allowing us to perceive both the softest breeze and the loudest storm without pain. Without this mental scaling, the world would be too loud, too bright, and too vast to comprehend. By folding multiplication into addition, we find a way to fit the infinite scale of the universe into our quiet, everyday experience. It is a quiet bridge between the tiny and the massive. It allows us to hold the stars and the dust in the same steady gaze. Electromagnetism. Imagine standing in the dark, holding a magnet. You cannot see the field stretching out from it, but you know it is there, pulling silently on a piece of iron. Now imagine flicking a light switch. An electric current flows, warming the bulb until it glows. For a long time, we thought these were separate things. In the quiet of the 19th century, in the year 1865, a Scottish physicist named James Clerk Maxwell brought together these mysterious forces. Before his work, scientists treated electricity and magnetism as entirely separate phenomena. You had static electricity that could make your hair stand on end, and you had magnetic rocks that could point a compass needle toward the North Pole, but no one knew how they connected. Maxwell changed that perspective forever. He unified these two forces into a single, beautiful concept, showing that electricity and magnetism are actually two aspects of the same electromagnetic field. He did this by writing down 4 elegant equations. These mathematical descriptions showed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. They feed into one another, creating a wave that can travel through space. When Maxwell calculated the speed at which these waves would travel, he made a startling discovery. The speed matched the speed of light. He realized that light itself is not a separate substance. Light is an electromagnetic wave, a ripple traveling through the invisible fields that fill the universe. For thousands of years, humans only knew about the light they could see with their eyes. Maxwell's work revealed that visible light is just a tiny slice of a vast, invisible spectrum. The colors we see are part of a much larger family of waves. This spectrum extends far beyond our vision, including radio waves, microwaves, and X-rays. All of these waves travel at the exact same speed, differing only in how quickly they vibrate. This mathematical unification changed the course of human history. It was a triumph of mathematical prediction, where the equations pointed to a reality that had not yet been seen. Later, physical experiments confirmed that these waves existed exactly as Maxwell predicted. This work laid the foundation for almost all modern technology, from radio and radar to wireless communications. It also set the stage for Albert Einstein to rethink our ideas of space and time, leading to the theory of relativity. If light waves could travel across empty space, what happened when humans learned to settle down and manipulate the ground beneath them for food? Plant domestication. Let us travel back about 10,000 years to a region we now call the Fertile Crescent. The world was warming, the glaciers were retreating, and humans were wandering, gathering what they could find. Among the wild grasses grew a type of wheat called einkorn. Normally, when wild wheat matures, the stem becomes brittle and shatters. This allows the seeds to scatter on the wind, spreading the plant to new soil. It is a brilliant strategy for the plant, but a difficult one for a hungry human trying to gather dinner. If you touch the plant, the seeds fall to the earth and disappear into the soil. Then, a subtle change occurred. A tiny genetic mistake, a mutation, caused a few plants to keep their seeds firmly attached to the stalk, even when ripe. In the wild, these plants were evolutionary dead ends, because their seeds could not fall and sprout on their own. But to an early gatherer, these mutant stalks were a treasure. They could be harvested easily without the grains spilling onto the dirt. People began collecting these specific seeds, carrying them back to their camps and planting them on purpose. Those early humans were stepping into a silent partnership. By selecting only the plants that held onto their seeds, humans altered the genetic destiny of wheat. We call this process artificial selection, a human-driven evolution that changed the shape of life on Earth. This partnership went both ways. As we shaped the plants, they shaped us. Wild wheat did not require permanent attention, but cultivated wheat did. To protect their crops from pests, weather, and other animals, humans had to stay put. We stopped wandering. We built sturdier shelters, then fences, and eventually permanent villages. The plants anchored us to the soil. We worked for them, clearing land and carrying water, and in return, they provided a reliable source of food. This new way of living changed everything. For the first time, human communities could produce more food than they needed to survive immediately. This surplus changed the fabric of society. When everyone did not have to spend every day searching for food, some people could explore other paths. Some became builders, others became weavers, and others began to work with metal. To track the storage of all this extra grain, humans developed the first forms of writing and arithmetic. Clay tablets were marked to count bushels of wheat, laying the foundation for written history. As populations grew, simple villages expanded into the first cities. Hierarchies formed, laws were written, and civilizations arose. All of this started because someone chose to plant a mutant seed that refused to let go. In our effort to domesticate the wild grasses of the earth, we ended up domesticating ourselves. Place value notation. Imagine sitting at a wooden table under the dim glow of a candle, trying to add two numbers together. In your left hand, you have the number 1124, written in Roman numerals using the letters M, C, X, I, and V. In your right hand, you have 456, written as C, D, L, V, and I. If you want to combine these two values, you cannot simply line them up. There are no columns to guide your eyes, and there is no simple way to carry a digit over. For centuries, doing basic math with these symbols required a specialized counting board or an abacus, along with years of training. Most people could not do it at all, relying instead on professional calculators to settle accounts. Then, a quiet revolution traveled from India through the Middle East and into Europe. It was the introduction of place value notation. With this system, we only need 10 simple symbols, from 0 to 9. The magic lies in where those symbols are placed. When you write the number 152, the digit 5 represents 50, rather than simply 5, because it sits in the second slot from the right. If you move that 5 one space to the left, it represents 500. Each step to the left multiplies the value of the symbol by 10, while each step to the right divides it. This simple shift changed daily life. Anyone with a scrap of paper and a charcoal stick could now line up numbers in neat columns. You add the right column, carry the extra into the next slot, and proceed. Calculations that once took minutes of moving beads on a wooden board could now be completed in seconds by a child. By linking the value of a symbol to its physical position, humanity unlocked a language that could express any size of quantity, from the tiny grains of sand on a quiet beach to the silent distance between distant stars, using the exact same 10 basic marks. It took mathematics out of the hands of elite scholars and gave it to merchants, builders, and everyday people. A simple shift of symbols on a page opened up the modern world, paving the way for all the calculations that construct our cities and map our skies today. Public sanitation. During the unusually hot summer of 1858, the City of London came to a complete standstill because of a smell. The River Thames had become an open sewer, and the intense heat wave turned the water into a thick, bubbling soup of human waste. The stench was so overwhelming that it was named the Great Stink. In the Houses of Parliament, right on the riverbank, desperate politicians soaked their curtains in chloride of lime to block the odor. They even discussed moving the entire government out of the city to escape the fumes. For centuries, people lived with the belief that bad air caused disease. But the sheer weight of this crisis forced a massive change in how we build and maintain cities. An engineer named Joseph Bazalgette proposed a solution that seemed almost impossibly large at the time. He designed a massive underground network of brick-lined sewers. Over 82 miles of main intercepting tunnels were dug beneath the busy streets of London, along with more than 1,000 miles of smaller local sewers. This system was designed to collect the waste of millions of people and use gravity to carry it far downstream, away from the intake points where the city drew its drinking water. Bazalgette used flat, oval-shaped bricks that allowed water to flow smoothly, preventing blockages. The scale of the work was unprecedented, requiring millions of tons of concrete and hundreds of millions of bricks. By physically separating the water people drank from the water they used to wash away waste, this engineering marvel quietly saved countless lives. Before this network was built, regular outbreaks of cholera swept through the crowded neighborhoods, killing thousands of residents in a matter of weeks. Once the new sewers began operating, those outbreaks stopped. Clean water made city life bearable and doubled urban life expectancy over the next few decades. This achievement provided practical proof that water, not bad air, carried the invisible agents of disease, which helped establish the value of germ theory. But more than that, it proved that the health of a society depends on the invisible pipes beneath our feet. We built a silent shield under the earth, allowing modern cities to grow and thrive without destroying themselves. Refracting glass. If you hold a handful of common beach sand, it feels rough, dry, and simple. Yet, if you heat that sand until it melts, it cools into clear, smooth glass. If you then grind and polish that glass into a precise, gentle curve, something extraordinary happens to the light passing through it. The light bends, focusing in ways our eyes cannot do on their own. By shaping this simple material, we created the lens, and with it, we completely transformed the scale of human thought, opening up windows to things that were previously hidden from our view. In the year 1610, Galileo Galilei pointed a tube containing 2 of these glass lenses toward the night sky. He looked at the planet Jupiter and saw 4 bright points of light dancing around it. These were moons, orbiting another world, which provided the physical proof needed to support the model of Copernicus, showing that the Earth was not the center of all motion. A simple curve of glass pushed our minds out into the solar system, making the distant cosmos feel close and real. A few decades later, a shopkeeper named Antony van Leeuwenhoek began grinding tiny glass lenses by hand, some no larger than a seed. He held a single drop of pond water up to one of his lenses and peered through. Instead of empty, clear water, he discovered a bustling, invisible world. He saw tiny, living creatures swimming, spinning, and living their lives in a space smaller than a pinhead. He called them animalcules. These discoveries dismantled an ancient assumption. For centuries, humans believed that the limits of our own senses were the limits of nature itself. We assumed that if something was too small to see, or too far to find, it simply did not exist. Glass lenses showed us that we live between 2 massive hidden worlds. One is vast and distant, while the other is microscopic and close. Our eyes only show us a small fraction of reality, and a simple piece of curved glass was the key that unlocked the rest. It taught us to look deeper, past the edges of what our eyes can naturally see. Neuroplasticity. Is your adult brain a fixed circuit board set in stone, or is it more like clay, that changes shape with every action you repeat. For a long time, science believed that once you reached adulthood, your brain was fully wired and done changing. It was thought to be a static machine, slowly wearing down over the years. But we now know this is not how it works. Your brain is dynamic, constantly reshaping its structure based on how you live. Every thought you think, every skill you practice, and every memory you form alters the physical pathways in your head. Think of your brain as a dense forest. If you walk the same path every day, that path becomes clear, wide, and easy to travel. In your brain, this is how connections grow stronger through use, creating a stable, well-worn trail. When you repeat an action or focus your attention, the signals between your brain cells travel faster and more efficiently. On the other hand, if you stop walking a path, the forest slowly grows back over it. Your brain naturally clears away the pathways that are no longer active, keeping the system clean and efficient. This balance of building up and clearing away goes on throughout your entire life, allowing you to adapt to new challenges. This physical restructuring happens even in adults, and one of the most famous examples of this involves the people who drive the black cabs of London. To get their license, these drivers must memorize 25,000 streets and thousands of landmarks. It takes years of intense study. Scientists scanned the brains of these drivers and discovered a physical difference. The area of the brain responsible for spatial memory, called the posterior hippocampus, had physically grown larger than in the average person. The demanding task of navigating that complex city had physically reshaped their brains. Your mind is not a passive passenger in a fixed machine. Your mental focus actually guides physical changes in the physical structures of your brain. By choosing where to direct your attention, you are actively sculpting your own neural pathways. If our experiences can change the physical connections in our brains, could the environment also alter the way our genes read themselves without changing our DNA? Epigenetic expression. Imagine two people born on the very same day, sharing the exact same genetic blueprint. They are identical twins. In their early years, they look and act almost exactly alike. But as the decades pass, their paths diverge. One twin remains healthy and active, while the other develops a chronic condition. If their genetic code is identical, we have to ask why their bodies took such different paths. For a long time, we believed that our genes were a fixed set of instructions, written in stone at the moment of our birth. We thought of our genetic code as a blueprint that dictated everything about our health and future. But we now know that the story is much more dynamic. Within every cell of your body, there is a complex library of instructions. But a blueprint is only useful if someone reads it. This is where chemical tags come into play. These tags sit on top of your genes, acting like tiny light switches or volume dials. They do not change the genetic code itself, but they decide which instructions are read and which ones are ignored. Some switches are turned all the way up, while others are silenced completely. This process is called epigenetics, which translates to on top of genetics. It is the language your body uses to speak to your genes, translating your life experiences into biological action. The food you eat, the air you breathe, the amount of stress you carry, and even the warmth of the relationships you have can change these switches. A stressful period in your life might turn a specific switch on, while a healthy diet might turn another one off. We are not simply passive products of our ancestry. The lives we live and the environments we create actively shape how our genes express themselves. This means that our experiences can even leave a biological signature that gets passed down to future generations. The choices you make today write new notes in the margins of your genetic library. It is a quiet, continuous conversation between your daily experiences and the very core of your biology, shaping who you are one moment at a time. Feedback loops. During a quiet night in a still house, a small box sits on the wall. This is a thermostat. It is listening to the air. If the temperature drops below 68 degrees, a switch clicks. The furnace hums to life, blowing warm air through the vents. As the room warms up, the thermostat feels this change. When the temperature reaches 69 degrees, the switch clicks again and the furnace goes silent. This is a loop. The output of the system, which is heat, goes back into the system as information, telling it what to do next. We call this a negative feedback loop. The word negative does not mean bad. It means the system works to counter change. It fights against deviations to keep things steady. Your own body does this every single second. If you get too hot, you sweat to cool down. If you get too cold, you shiver to generate warmth. It is a constant, gentle tug of war that keeps you alive. Without this constant balancing act, our bodies would quickly fail and cease to function. But there is another kind of loop, one that does not seek balance. This is positive feedback, where a change is amplified instead of countered. We can observe this when a microphone is placed too close to a speaker. A tiny sound goes into the microphone, comes out of the speaker louder, goes back into the microphone, and gets amplified again. Within seconds, this loop builds into a deafening shriek. We see this in our daily lives and in the wider world. In financial markets, if people see a stock rise, they run to buy it, which drives the price even higher, attracting even more buyers. This is how bubbles form. In climate systems, as global temperatures rise, ice at the poles melts. Because ice is bright white, it reflects sunlight back into space. When it melts, it exposes dark ocean water, which absorbs more heat, causing even more ice to melt. These loops are the invisible gears of our world. They keep our hearts beating at a steady pace, yet they also carry the power to push systems into wild, unpredictable behavior. They teach us that nothing exists in isolation. Everything we do and everything around us is constantly talking to itself, adjusting and changing in an endless conversation. Distributed networks. Think about sending a simple letter to a friend who lives across the country. In the past, that letter traveled to a central post office, then to a regional hub, and finally to its destination. If the central hub closed, the letter stopped. Now, imagine sending a digital message instead. The moment you press send, the system does something strange. It chops your message into tiny fragments, like cutting a letter into pieces. Each piece gets labeled with the destination address and a sequence number. Then, these pieces are thrown into a vast web of interconnected computers. One piece might travel through a server in Seattle, another through Chicago, and a third through Atlanta. They take whatever path is open at that exact millisecond. If a cable in Denver is suddenly cut, the remaining pieces detour around the blockage. They do not care which path they take, only that they keep moving. When they all finally arrive at the destination computer, they gather together, check their sequence numbers, and assemble themselves back into your original message. It is a messy, chaotic way to travel, but it is highly resilient. This is a distributed network. Unlike a centralized system with one powerful leader, or a decentralized system with a few major hubs, a distributed network has no single heart. There is no central point of failure. If you destroy one node, the rest of the web adapts instantly. The traffic flows around the damage. This design was born during the Cold War, when researchers wanted a communication system that could survive a physical attack. They realized the safest way to protect a message was to make it homeless, constantly moving through a crowd of equals with no single place to target. This engineering choice brought a quiet revolution in how we think about order and control. For thousands of years, humans organized their world like pyramids. We had kings, generals, and bosses who sat at the top, directing everything below. Power flowed down, and information flowed up. We assumed that without a central authority, there would be only chaos. We built our systems to be strong and rigid, believing that was the only way to keep them from breaking. A distributed network proves that order can emerge from the bottom up. There is no main computer directing the traffic on the global web. Every node makes its own local decisions, choosing the fastest path for the next packet of data. It is a peer-to-peer system, a collaborative mesh where cooperation happens without a boss. This shift from top-down control to shared responsibility shapes how we think about modern movements, financial systems, and even our own brains, which route thoughts across billions of interconnected neurons without a single master cell. It suggests that strength lies not in rigid pillars, but in the flexible, silent connections between us all. The interior Earth. We walk on a thin crust, a cold stone shell that feels permanent and solid. Yet beneath our feet lies a dark, silent depth we can never touch, a place of intense heat and crushing pressure. In 1906, a scientist named Richard Dixon Oldham was studying the vibrations of earthquakes. He noticed that when the ground shook on one side of the planet, the waves did not travel straight through to the other side. Instead, they bent, leaving a strange shadow where no vibrations could be felt. This shadow revealed that deep inside the planet lies a giant core, hidden from view. To understand this hidden world, we have to listen to the planet speak. When an earthquake happens, it sends two kinds of waves through the dark ground, acting like a giant sonar system for the deep earth. The first kind are compressional waves, which push and pull like an accordion. These waves can travel through anything, solid stone or liquid fire. The second kind are shear waves, which move side to side like a wriggling snake. These side-to-side waves can only travel through solid rock. They stop completely when they hit liquid, unable to pass through the fluid depths. By listening to these silent vibrations, scientists mapped the giant interior. Beneath our thin crust is a massive mantle of hot silicate rock that flows like thick tar over millions of years. Below that lies the outer core, a vast ocean of liquid iron. In 1936, a Danish scientist named Inge Lehmann discovered that inside this liquid ocean lies a solid heart, a giant ball of iron and nickel crushed solid by the weight of the world, a sphere almost as hot as the surface of the sun. This layered giant has existed for billions of years, keeping us safe while we sleep. The liquid iron moves and spins, creating the magnetic shield that protects our atmosphere from the cold wind of space. We live our lives on a thin, fragile skin, floating above a deep, dark furnace of liquid metal and solid iron that has been burning since the very beginning of the world. Underneath us, the Earth is alive with heat, a reminder of the ancient forces that shaped our home in the cold dark of space. The placebo effect. Imagine a crowded, dimly lit military hospital tent during the Second World War. The year is 1943. An American doctor named Henry Beecher is treating soldiers wounded in heavy fighting. The air is thick with dust, and the medical resources are running critically scarce. He runs out of morphine, the powerful painkiller needed for surgeries. The injured men are in agony. Desperate to ease their suffering and keep them calm, a nurse fills a syringe with simple salt water and injects it, telling the soldier it is a strong dose of medicine. To the doctor's surprise, the soldier calms down almost immediately. His heavy breathing slows, and his pain eases. Henry Beecher keeps trying this simple method, and he discovers that about 40% of the wounded men report real, lasting relief from a simple injection of sterile water. This simple observation changed modern medicine forever. It proved that a belief can alter our physical reality. When we expect a medicine to heal us, that expectation triggers actual changes inside the brain. It is like turning a key in a lock. The brain begins to produce its own natural painkillers, called endorphins, and releases dopamine, a chemical linked to reward, hope, and relief. These are not imaginary feelings or tricks of the mind. They are real, physical chemicals flooding the bloodstream, slowing the heart rate, and cooling down painful inflammation. The body is acting on the quiet belief that it has received help, and it responds by manufacturing the cure from within its own pharmacy. For a long time, we viewed the mind and the body as two entirely separate entities, like a driver sitting inside a car. But this phenomenon reveals they are a single, unified system. What happens in our thoughts is instantly translated into physical biology. An expectation is more than an abstract idea. It is a physical event that reshapes our internal chemistry. When the mind anticipates recovery, it sends a signal to the body to start repairing itself, altering our heart rate and even our immune response. Our unconscious expectations hold a quiet, steady power over our physical state, rewriting our biology without us ever realizing it. If our expectations can influence the chemistry of our bodies, what drives the fundamental engine that powers all life on our planet? Photosynthesis. A single green maple leaf hangs from a branch outside in the quiet night. Right now, it rests in the darkness, still and silent. But when the sun rises, that leaf becomes the site of a profound cosmic translation. It reaches up toward the morning sky, catching packets of light that have traveled 93 million miles through the cold void of space. The leaf takes this starlight and uses it to perform a kind of ancient alchemy, splitting water molecules apart and pulling carbon dioxide from the air to build simple sugars. Inside the leaf, within microscopic chambers, there are tiny green pigments called chlorophyll. When a packet of light, which we call a photon, strikes these pigments, it acts like a hammer hitting a bell. It rings with energy, sending a tiny electrical current through the plant cells. The leaf uses this current to charge up two vital energy-storing molecules. Scientists call these molecules adenosine triphosphate and nicotinamide adenine dinucleotide phosphate. You can think of them as microscopic rechargeable batteries. As the plant builds these batteries, it splits water molecules, keeping the hydrogen and releasing the oxygen back into the breeze. Once these molecular batteries are charged, the leaf enters the next phase of its work. It does not even need light for this part. Using the stored energy, the leaf takes carbon dioxide, a gas we exhale and that drifts in the wind and chains the carbon atoms together. It combines them with the hydrogen from the split water. Through this delicate dance, the leaf constructs glucose, a simple sugar that serves as the building block for the entire plant. From this single sugar, the plant builds its roots, its trunk, its flowers, and its seeds. Every piece of wood in a towering forest was once nothing but air, water, and sunlight, woven together by this silent process. That oxygen released during the water-splitting phase is simply a waste product to the leaf, but it is the very breath of life for almost every living creature on Earth. Long ago, before plants existed, the atmosphere of our planet had virtually no oxygen. The world was quiet, home only to simple, single-celled organisms hiding in the deep ocean. Then, ancient ancestors of these green leaves began using sunlight to split water. Over vast stretches of deep time, they flooded the skies with oxygen, completely transforming the chemistry of the Earth. They created the protective shield of the ozone layer and paved the way for complex life, for animals, and eventually, for us. Every breath we take connects us directly to this green engine. Nearly all the energy driving the entire biosphere is actually captured starlight. The energy that moves your muscles, the warmth in your skin, the power that runs the thoughts in your brain, all of it started as light from our nearest star. When we eat, we are consuming stored sunlight that plants gathered and packaged. We are, in a very literal sense, creatures sustained by the quiet work of green leaves, breathing in the sky they created for us, living on light. Superconductivity. Let us think about a small, dark ceramic disk sitting in a shallow bath of liquid nitrogen. A thick cloud of cold white vapor rolls slowly over the edges of the dish. Above this freezing disk, a tiny metallic magnet floats in mid-air. It does not fall, and it does not fly away. It is locked in place, hovering silently as if held by invisible fingers. If you gently tap the magnet with a fingernail, it spins in place, perfectly stable, suspended in the empty space above the cold surface. This quiet defiance of gravity happens because of a sudden, dramatic change in how electricity behaves. When certain materials are cooled to extreme temperatures, close to the absolute cold of deep space, they undergo a quiet transformation. They enter a state called superconductivity. In normal wires, electricity faces constant resistance. Moving electrons bump into vibrating atoms, like people trying to run through a crowded, chaotic room. This constant bumping slows them down and generates heat, wasting energy. But inside a superconductor, the rules of the game change. As the temperature drops past a critical point, the atoms in the material quiet down and align. The electrons do not travel alone anymore. They pair up into couples called Cooper pairs. These pairs glide through the material in perfect harmony, moving together like dancers across an empty floor. Because they are paired, they no longer bump into the atoms around them. They flow with zero resistance, finding a path of absolute ease. As a result, an electric current started in a superconducting loop will circulate forever. It will flow for days, years, or even centuries, without losing a single watt of power as heat. If we could build power grids from these materials, we could transport energy across entire continents without losing any of it along the way. Today, this frictionless flow of electricity is what powers the powerful magnets inside magnetic resonance imaging scanners in hospitals, helping doctors see deep inside the human body. The floating magnet is trapped by this effortless flow, held in place by a phenomenon known as the Meissner effect, which expels magnetic fields. It is a glimpse of a world without friction, a quiet reminder of what happens when we cool the universe down to its quietest limits. Plate tectonics. In 1912, a German meteorologist named Alfred Wegener studied a map of the world and noticed something strange. The east coast of South America and the west coast of Africa looked like two puzzle pieces that had drifted apart. When he looked closer, he found matching fossils of ancient plants and reptiles on both sides of the vast ocean, creatures that could never have swum across the salt water. He proposed a wild idea, that the continents were once joined together and had somehow drifted across the globe. For decades, other scientists laughed at this idea because nobody could explain how a massive continent could slide across the solid ocean floor. They believed the oceans and land were permanently fixed in place. The answer lay deep beneath our feet. Far below the surface, radioactive elements decay inside the warm core of our planet, releasing immense heat. This heat warms the thick rock of the mantle above it, causing the rock to rise slowly, like warm soup in a pot on a stove. As it reaches the cooler upper layers, it spreads out, cools down, and sinks back toward the center. These giant, slow loops of rising and sinking rock are called convection currents, and they move with immense force. They act like a conveyor belt, carrying the rigid outer crust of the Earth along with them. This outer crust is not a single solid shell. Instead, it is a collection of massive pieces called tectonic plates. The plates float on a hot, semi-liquid layer of rock, moving in response to the deep currents below. These plates move at about the same speed that your fingernails grow, a few centimeters every year. Yet over millions of years, this slow movement changes the entire face of the planet. When two plates crash into each other, the land has nowhere to go but up, building towering peaks like the Himalayas, which are still growing taller every single day. When plates pull apart, they tear open new ocean basins, creating space for new seas to form as magma rises to fill the gap. When they slide past one another, they stick and then slip, releasing energy that shakes the ground. The ground beneath us is not static. It is a slow, living puzzle, constantly rebuilding itself while we sleep. Conservation of energy. When a speeding car slams on its brakes and comes to a sudden, complete stop, where does all that movement go? 1 second, thousands of pounds of metal are rushing forward at 60 miles an hour, and the next, everything is completely still. That massive amount of motion cannot simply vanish into nothing. It turns out that the movement is not lost. Instead, it changes its shape. As the brake pads squeeze against the spinning wheels, the energy of the motion rubs off, turning into heat. If you were to touch the brakes right after that stop, you would find them burning hot. Some of the energy also escapes as the sharp squeal of the tires, sending ripples of sound through the night air. This simple moment reveals one of the most fundamental rules of our universe, known as the first law of thermodynamics. It tells us that energy is a survivor. It cannot be created from nothing, and it cannot be destroyed. It can only change its form, wearing different masks as it moves through the world. Think of the life of a single spark. The energy starts locked away in the chemical bonds of a piece of wood. When you light a fire, that chemical energy transforms into the bright glow of light and the warming heat that you feel on your skin. That heat warms the air, causing air molecules to dance faster and spread out. The energy does not disappear. It just disperses into the room, becoming less concentrated and harder to use, even though every single bit of it is still present in the atmosphere. This steady decline in the usefulness of energy happens all around us, meaning that while the quantity of energy never changes, its quality slowly breaks down over time, spreading out into the cold background of space. Because of this constant shifting of forms, the total energy budget of the universe is locked at a fixed amount forever. Every ray of sunlight, every gust of wind, and every heartbeat is just a new expression of that original, ancient budget. We live in a cosmos where the currency is constantly traded, from potential energy to kinetic energy, from chemical to electrical, but the bank account of the universe never gains or loses a single cent. It is a closed system, locked at a fixed amount forever, quietly moving from one state to another while we watch. Cellular Theory. In the winter of 1665, a curious man named Robert Hooke sliced a sliver of cork, thin enough to let light pass through. When he looked at it, he did not find a solid wall. Instead, he saw a delicate grid of tiny, empty boxes, resembling the small rooms where monks slept in a monastery. He called them cells. At the time, he thought he was looking at empty spaces, a mere oddity of bark. He had no way of knowing he had stumbled upon the basic building blocks of all living things. Decades passed before we understood that these chambers were not empty at all. They are active, bustling cities of life, containing their own microscopic machinery. This realization grew into a beautiful, simple idea. Every living creature, from the towering redwood to the smallest moss, is made of these tiny units. Every cell comes from another cell, a direct link in a chain of life that stretches back billions of years. You are not a single, solid object. You are a vast cooperative colony of roughly 30 trillion individual cells, all working together in the dark to keep you breathing. They coordinate their efforts without any central planner telling them what to do. Each cell has its own specific job. Some carry oxygen through your veins, some defend against foreign invaders, and others store memories in the brain. They are born, they perform their duties, and they quietly divide to make new ones. This structure tells us that life builds complexity from the ground up. It starts small, with simple components that learn to work in harmony, creating the walking, talking, thinking person that you are. It is strange to think that you are made of trillions of tiny living entities, each one living its own quiet life inside you. They are the silent workers that maintain your heartbeat, heal your skin while you sleep, and turn your food into energy. We are walking ecosystems, held together by a shared purpose. Every single breath you take is a coordinated effort of billions of tiny engines, all hummed to the same quiet frequency. But even as we map the tiny cells that build our bodies, we must look up and ask, how far into the vast night sky can we actually see? The cosmic horizon. Turn your gaze upward on a clear night, far beyond the streetlights, toward the faint smudge of the Andromeda Galaxy. The light entering your eyes at this very moment left those distant stars 2.5 million years ago. You are not looking across space so much as you are looking backward through time. You see the galaxy as it was when early ancestors of humans were first walking the Earth. Every photon carrying that image has been traveling through the cold void for millions of years, just to end its journey on your retina. The night sky is a tapestry of different eras, all overlapping in the present moment, showing us things as they were, not as they are. This connection between distance and time reveals a profound boundary. Because the universe has a finite age of 13.8 billion years, and because light travels at a set cosmic speed, there is a hard limit to how far we can see. Imagine a messenger who started running at the moment of creation. No matter how fast that messenger runs, they can only have covered a certain distance by today. The same is true for light. The light from objects too far away has simply not had enough time to reach us yet. They are hidden behind a curtain of time, existing in a space we cannot access. This boundary is what we call the cosmic horizon. It is a soft, invisible wall that wraps around us in all directions, defining the limits of our observable world. Beyond this horizon, there may be an endless stretch of space, countless more galaxies, and stars we will never name. But because of the age of our universe, those places are completely cut off from us. Their light is still on its way, traveling through the darkness, and some of it will never reach us, because the space between us is expanding. Think about this limit. Even if we had infinite time, and even if we built telescopes of unimaginable size, we would still run into this absolute wall. There is a portion of the cosmos that is forever closed to us. Not because our technology is lacking, but because the universe itself has a beginning and a speed limit. It is a quiet reminder of our place in the grand design. We live in a bubble of light, surrounded by a vast, silent sea of the unseeable. The cosmic horizon is the ultimate boundary of human knowledge, a line in the sand drawn by physics, reminding us that some secrets of the cosmos will remain forever kept in the dark, untouched by human eyes, drifting in a silence we can never break.